Okay, and now we have Mauricio Barba da Costa, who is going to talk about language model probabilistic programming for improving autoformalization.
All right, thank you for that introduction. My name is Mauricio. This is our work on autoformalization using language model probabilistic programming. This is joint work with lots of people who are in this room right now. Yeah, so without further ado, I'll start by introducing what autoformalization is. And to do that, I'm going to start with this example of the Kepler conjecture. In the year 1611, Johann Kepler conjectured that the optimal sphere packing in 3 dimensions is this hexagonal close packing, which is this configuration of balls that kind of shows up in nature pretty often at the grocery store. It's how cannonballs are configured. In 1998, Thomas Hales proved the conjecture. In 2014, the FlySpec project formalized the proof in Isabelle and actually found holes in the proof that had to be revised. And then in 2025, multiple companies are now working on formalizing large swaths of informal math into LeanFor using LLMs. The key word here is formalize. Okay, so what I mean by formalize is this translation task where we're going to start with natural language and convert that into a formal theorem-proving language so that we can defer the certification of some code to a machine as opposed to a person. So autoformalization is going to be like a pipeline for doing this formalization in a way that involves minimal human intervention. And this is important because humans often make mistakes, right, as we saw in the example, that machines are a little bit more robust to. But this is challenging because natural language is often very underspecified. Natural language has a lot of shorthand and has a lot of abbreviations that have to be spelled out very explicitly for LeanFor. Because LeanFor is very pedantic. So if we're going to create an autoformalization pipeline, one way that we can do this is by using a prompt harness. I should say in the examples or in the different attempts at doing this that I'm going to consider, I'm only considering inference time strategies for doing this, so things that don't involve training. So your first attempt at doing this might be making a prompt harness, right? And this would involve passing many text signals into an LLM, like make the informal statement match the original, do not make mistakes or else, only output lean. But this is challenging, okay, because when you pass multiple of these text signals into the LLM, you could push it into weird parts of its distribution, and you can alter the performance in unpredictable ways. Also, prompting on its own often isn't enough to get lean or an LLM to output correct lean. And this is because sometimes the LM is defiant. It'll intersperse natural language with its lean code output. And oftentimes the lean output that it does make is not well typed. And that's because it gets the syntax wrong or because it doesn't pass the type checker and so forth and so on. Your second attempt at making an autoformalization pipeline might involve locally constrained decoding. And this involves, at every step of the LM generation process, masking the tokens in the vocabulary that otherwise would call the LM to deviate from the target grammar. And so when you use this sampling procedure, the samples that you get fall according to this distribution that I'm calling QLCD. So the notation here is QLLM is the base LM distribution, J is going to be the set of strings that are well typed, and then J bar is the prefixes of all strings that are well typed. The Z's under each of these QLLMs are the normalizing constants that you need in order to adjust for the tokens that you've excised from each of the token generation steps. So the challenge here is that because we're dividing these QLLMs by multiple of these Z's, we're distorting the base distribution QLLM, and this can be quite substantial. And so when you generate samples from QLCD, the probability assigned to those samples by QLLM can potentially be very low, and that's correlated with poor performance in downstream tasks. Now, our third attempt is going to involve using GenLM, which is a language model probabilistic programming framework that's going to allow us to sample from the unnormalized distribution QLLM times phi. Phi is what are known as these potentials, and phi is going to be just a real valued function where we assign some real number to the token sequences that are generated by an LLM. And this is a convenient programming model to have, right? If I wanted to do constrained decoding, what I could do is I could create a potential phi that's going to assign 1 when x is well typed and 0 otherwise. So the challenge about sampling from this distribution directly is that this normalizing constant z is intractable because it involves taking a sum across all of the token sequences that an LLM could produce. However, the advantage of sampling from G is that samples from this distribution are much more closely calibrated with those from the base distribution QLLM. So the workaround that GenLM uses to sample from this distribution is it uses sequential Monte Carlo to generate samples approximately from G as opposed to exactly. And so sequential Monte Carlo is going to go through the following steps. Okay, so if we start with a prefix of an LLM output, we're going to generate multiple candidate extensions of that prefix. We're going to weight these. If I have a binary potential, like one that does constrained decoding, these weights are going to be just 1 or 0. And in general, if the potential was continuous, these weights would correspond to the importance weight. And then we're going to resample proportional to the importance weights that we assign to each of these extensions. And then we're going to repeat this process over and over. So for the particular case of autoformalization using GenLM, our potential phi is going to be composed of the product of 2 components. The first is going to be phi WT, or phi well typed, which uses incremental type checking to steer the LLM generation to output well typed lean code. And the way that we do this is by affixing a dummy conclusion and proof at certain safe checkpoints of the LM generation, and then passing that into the lean4 checker so that we have an incremental type checking signal. And then the second potential that we're going to use, phi CC, or phi cycle consistency, is going to enforce cycle consistency between the informal and formal statements. Cycle consistency is a heuristic that's used in translation that basically says that between 2 translations, the better one is the one whose back translation is more closely similar to the original statement. The way that we're going to encode this as a potential is in the following way. We're going to start with an informal statement. We're going to make a couple formalization attempts. And then we're going to, for each formalization attempt, create a new prompt to an LLM that's going to request that it informalize the formal statement. Phi CC is then going to be assigned the probability of the original informal statement under this informalization prompt. So here's a summary of the pipeline. We're going to start with an informal statement. We're going to make multiple candidate formalizations using GenLM that are steered to be well-typed lean code. And GenLM is also going to upweight the sequences that satisfy cycle consistency. And then finally, in the end, we're going to sample one of the sequences according to its importance weight. And that's going to be our final output of our autoformalization pipeline. So here are what the results look like. I'm happy to share more details about the benchmarks and about some of our methodology during the poster session. But for now, the big kind of TLDR is we're able to get better accuracy than a baseline using fewer tokens and less time as well. So the key takeaways here are that GenLM offers a very convenient programming model for representing these decoding strategies that simply involves defining these potentials. And it's very practical, even in kind of reasonable use cases. So yeah, that's the end of my talk. Thank you.
Any questions? Yeah.
One of your slides shows that you generate some term with the probability of product of that is well typed and the other term. But sometimes if you, maybe the prefix of the term is not well typed, but if you continue, you'll get well typed term. So when did you evaluate if the term is well typed in the generation process? Did that introduce a problem for you?
Yeah. So we do these checks at these safe checkpoints, which happens to be, for instance, after a variable is defined or after like a hypothesis is defined in Lean, and that's denoted by like a a closed parenthesis, right? And so once you reach an instance of a closed parenthesis, right, you're at kind of some intermediate level of the generation, and we affix a dummy conclusion and a dummy prefix, and that tells us, okay, this, at least everything up to here is well typed, right? So we kind of, so yes, it is possible that if you're, if you have code that's not well typed, it'll eventually salvage to something that's typed, but that doesn't end up being a problem with our use case because we do the constraining at these safe checkpoints. Yep.
A follow-on to that, does Lean, this is an honest question, I don't know, does Lean complain when you haven't unified metavariables? Because I would imagine, like, if you have your approach where you put in like a trivial statement, then there could be some unification, like you could have something that could be well typed as long as later on you put something in that makes metavariables unify. But without that, it wouldn't be well typed.
Yeah, it does complain about metavariables, and I've seen that be more of a case when you try to do incremental type checking when you're generating proofs. But I have to think a little bit more about this affects creating the specification for a proof as opposed to the proof itself.
Just one last question. So you didn't say what model you were using, because state-of-the-art models are super good at generating lean code right now without constrained decoding. So results are a little bit surprising.
Yeah. So we use a 70B model. So that was like DeepSeek, Llama, and it's from a couple years ago. I imagine the Claude and stuff that's been RLVR'd very heavily on Lean can probably do better now. But yeah.
Okay, thanks a lot.